God bless you all, and a happy 4th of July. Now, here they come. Here it comes. And that I love, stand beside us and guide us through the night with a light from above, from the mountain to the prairie, to the ocean, white with foam. God bless America, my home sweet home. That can fuddle you up.
We mourn 7 heroes: Michael Smith, Dick Scobie, Judith Resnick, Ronald McNair, Ellison Onizuka, Gregory Jarvis, and Krista McAuliffe. We mourn their loss as a nation together. The families of the 7, we cannot bear as you do the full impact of this tragedy. But we feel the loss, and we're thinking about you so very much.
The theme for this video is complexity. The shuttle was one of the most complex systems ever built. In order to meet its design goals, keep it simple wasn't really an option. There are 3 reasons I felt compelled to make this video. Number 1, this channel wouldn't exist without the shuttle. And not for the reasons you probably think. There is a suspiciously long chapter in this video that'll explain all. Number 2, over my lifetime I've followed a trajectory many of you will have too. Growing up, I thought the shuttle was the greatest engineering achievement of all time. Then I decided it was a waste of money and a death trap. In recent years, I've come to sit somewhere in the middle. The shuttle was flawed, but it was incredible, and I wanted to make that clear. Number 3, this may also be considered a prequel to my next video, which will be about Buran. Of course, both can be watched in isolation, but to avoid a typical Buran versus shuttle showdown, I decided to make this video first as a standalone discussion. I now appreciate everything the shuttle did for us, but I do not want to excuse its flaws. In this video, shuttle refers to the system as a whole. That not only includes the spacecraft, but the people who built it, their procedures and safety culture, and the many organisations required to get it off the ground. You'll not hear me say things like, if we put aside the 2 disasters, the shuttle was excellent, because the 2 disasters were part of the shuttle. Now before we begin, I did not want to make this video to just be a compendium of Scott Manley material. His videos are, in my opinion, the best source of shuttle content on YouTube. So for those wanting more technical detail, go and check out his channel. Real Engineering also recently made some excellent videos about the shuttle. Though I'm going to go into a lot of detail here, it might not be in the way you expect, and I aim to minimise any crossover with what's already out there on YouTube. Please check the subtitles if you think you spot a mistake. I'll add corrections there if and when they're pointed out to me in the comments. In 1969, NASA landed men on the moon, and then immediately faced an existential crisis. There'd be no more blank checks, which honestly is probably for the best. NASA needed to find their own way and to justify their existence. We're going to skip over the years of political wrangling because it's of no interest to me. But the end result was a demanding set of requirements for a new orbital vehicle. Many of these requirements originated from the Air Force, who NASA decided to partner with to secure funding. They included the capability to carry both crew and 29 tons of cargo to low Earth orbit, and that cargo had to be carried in a 4.6 by 18 metre payload bay. They required the ability to launch on an almost weekly basis, requiring as much reusability as possible, and also an overall cost-effective program, also capable of launching commercial payloads. Emphasis there on cost-effective for those advocates of we should have just kept flying the Saturn V. These, along with other more specific requirements from the Air Force, limited the design of the new orbiter to a reusable spaceplane. The requirement for a spaceplane immediately locked in two major design constraints that have grave ramifications going forward. The first is a lack of a crew escape system. With the exception of a couple of Voskhod launchers in the 1960s, the Shuttle is the only orbital launch system ever built and flown with no means of crew escape. Many will claim it was possible via multiple ejection seats or a jettisonable crew compartment. It was not. This problem was studied extensively on multiple occasions. There was never a practical means to add a crew escape system to the Shuttle. NASA instead elected to design and operate the Shuttle with a stringent QA and QC process to ensure the chance of a catastrophic failure on launch was minimal. We'll get back to that. You know what? Listening back, I want to make my position about crew escape systems unambiguously clear, because it's gonna come up again later. I mentioned them in a previous video and actually had people arguing with me that escape systems aren't necessary. The Everyday Astronaut has a video about why SpaceX don't intend to use a crew escape system on Starship, and I think that's probably where most of these comments come from. I love the Everyday Astronaut, but I disagree with some of the conclusions in that video. And that's fine. It's completely fine to disagree on design philosophy. That happens all the time. Anyway, at the time of recording, humans have been launched to orbit on a total of about 350 occasions. In the relevant chapter of his video, when assessing past performance of escape systems, Tim points out that an escape system did or could have saved the crew in only 3 cases, or less than 1% of flights. He also points out there were just as many fatal flights where a crew escape system couldn't have saved the crew. Here's how I interpret those numbers. Let me present it differently. Here are all the orbital flights where the crew died. Here are all the orbital flights where a crew escape system either could have or did save the crew. So, based on our limited dataset, the chance of dying at any point during an orbital flight is cut in half if a crew escape system is present. Here's a visual representation of that conclusion. Do you see what happened there? Same limited dataset, but completely different but logically correct conclusions. A mixed signal. Keep that in the back of your mind, because boy is that going to come up again later in this video. Now, there is a case of an escape system firing on the ground and killing a member of ground crew. It happened nearly 60 years ago. Nevertheless, that's 1 fatality against 11 that were or potentially could have been saved by a proper escape system. So, my position is unambiguous. If you can use a crew escape system, use a damn crew escape system. To understand the second design constraint, we need to start building a shuttle stack. The high payload requirements, along with the mass of the orbiter itself, necessitated a novel and innovative approach. The Saturn V was already capable of getting 140 tons to orbit. It was able to do so in part due to the use of hydrogen and oxygen as the stage 2 and 3 propellant. Hydrogen is the most efficient fuel available for rocket launchers. By efficient, I'm referring to specific impulse, which is a measure of the amount of chemical energy that is converted to kinetic energy of the payload. I discuss specific impulse further in the video linked here. The shuttle orbiter, however, was huge compared to Apollo. It couldn't really sit on the top of the stage 2 propellant tank, which in itself would also have to be huge. Less ambitious spaceplane designs such as the Dinosaur and Dream Chaser were designed to be forward mounted, but this was simply not possible with the shuttle. So instead, it'd have to be strapped to the side of the propellant tank. And that's our second critical design choice. The fragile heat shield would be exposed at launch. For now, let's put the main engines to burn the hydrogen on the stage 2 tank itself. Apollo-era open-cycle engines would not suffice, however. To provide the necessary energy to reach orbit, something more efficient was necessary. And this required quite possibly the most impressive piece of engineering in the entire shuttle stack. The Space Shuttle main engines, or RS-25s, are, in my opinion, not just one of the most impressive feats of aerospace engineering of all time, they're one of the most impressive things humans have built, full stop. In this chapter, I'm going to build up a model of an RS-25, showing the flow paths of all the major components. The everyday astronaut has an absolutely outstanding video where he goes through various engine cycles. Obviously, I don't want to just repeat that, so we're going to go into some extra detail here. Prior to the shuttle, every large liquid-fueled engine in the US functioned like this. Fuel and oxidizer are combined and ignited in the combustion chamber to provide thrust. However, to get the propellants into the chamber, they require high-pressure pumps to force them in against the high pressure in the chamber itself. These pumps are driven by burning some fuel and oxidizer in a pre-burner to drive a turbine. This entire assembly is referred to as a turbopump. This is how most engines function even today, but it's not the most efficient design. The pre-burner is typically run fuel-rich to maintain an acceptable temperature. So the turbine exhaust contains unburned fuel. That's fuel that could otherwise have been burned in the main chamber. So to create a more efficient closed-cycle engine, we seek to feed the fuel-rich exhaust back into the combustion chamber to burn that extra fuel. Hydrogen is the ideal fuel for this. It produces water as an exhaust, so the fuel-rich pre-burner does not produce soot, which would clog the injectors into the combustion chamber. But there's an issue. Hydrogen and oxygen have wildly different densities. Liquid oxygen is 16 times more dense than liquid hydrogen. Using a common turbine to pump two completely different flow rates and densities just isn't going to work. We need separate pre-burners and turbines for the fuel and oxidizer. And that's just the beginning of the RS-25's complexity. You may have seen a flow diagram like this. It's intimidating, but give me a few minutes and you'll be able to understand this. Let's remove all the hydraulic and test lines. They're just here to open and close valves. We don't need these to understand the engine cycle. Okay, now I'll walk through the propellant flow paths. Let's start with the hydrogen pump. Fuel and a small amount of oxidizer are injected to the pre-burner to drive the turbine. This drives a 3-stage high-pressure pump, which takes low-pressure hydrogen and boosts it to around 45 megapascals. Some of this high-pressure fuel is directed through hundreds of small-bore pipes around the nozzle to cool it. The return path from the nozzle joins with a second output from the fuel pumps, and the high-pressure fuel is fed into the pre-burner. A third output from the pump is directed around the combustion chamber to cool it. Here, the fuel is vaporized and feeds into a low-pressure fuel turbine, which drives the low-pressure fuel pump, providing flow directly from the tank. For those familiar, that is an expander cycle. The RS-25 uses the expander cycle to drive the low-pressure fuel pump. Some of the vaporized fuel is fed back into the hydrogen tank in the external tank assembly. On reaching the fuel, this warm hydrogen expands and therefore provides pressure to the main fuel tank. Feeding back gaseous fuel to maintain pressure in this manner is referred to as autogenous tank pressurization. The RS-25 wasn't the first engine to employ this. The Titan managed it first. But this is just another layer of complexity to the system. The rest of the warm hydrogen is fed into a jacket around the hot gas manifold to cool it. The hot gas manifold contains the fuel-rich exhaust from the pre-burner and routes into the main combustion chamber, where the hot fuel is combined with liquid oxygen to provide thrust. So that's the fuel half. Now let's go through the oxidizer half. The oxidizer pump burns fuel output from the high-pressure fuel pump to drive the turbine. This spins up a 2-stage pump. Stage 1 boosts all of the incoming liquid oxygen to 30 megapascals. Most of this is fed directly into the combustion chamber. A small amount is tapped off and sent to the second stage of the oxidizer pump, which increases the pressure to 45 megapascals. high enough to force it into the preburners, allowing the combustion reaction to take place. Returning back to the 30 megapascal oxygen line, some of it is tapped off to drive the turbine for the low-pressure oxidizer pump, which extracts oxygen directly from the external tank. Hot oxygen is needed for tank pressurization, but with fuel being used for regenerative nozzle cooling, a dedicated heat exchanger around the hot gas manifold is required instead. The gaseous oxygen is fed back into the main oxidizer tank, providing autogenous pressurization. Some of this gaseous oxygen is also fed into an accumulator tank, which is hydrostatically connected to the low-pressure oxygen flow. This dampens any pressure oscillations in the oxidizer flow, preventing an effect known as pogo oscillation. The RS-25 also houses pressurized helium used for purging during an emergency shutdown and to pre-charge the pogo suppression accumulator. More interestingly, this helium is fed into a cavity between the oxidizer preburner and the oxygen pump. This forms an interpropellant purge seal, preventing oxygen coming into contact with the hot fuel-rich gas, which had caused an explosion in the pump. And with that, we have the most complex rocket engine ever flown. Some may argue the SpaceX Raptor is more complex, but it isn't. I'm not saying more complexity is necessarily better, but the use of hydrogen as a fuel in a closed cycle makes the RS-25 the most efficient main engine ever flown to this day. Oh, and when they ignited, they looked like this. I could literally talk for an hour about this single video clip. That absolutely beguiling pattern around the exhaust perimeter is the low pressure flow separating from the nozzle walls. Much consideration was given to avoid the nozzle shaking itself apart as a result of this. Such a large nozzle is required as it has to perform from sea level all the way to the vacuum of space. You can see it flexing as the flow separation is overcome. A design compromise to help mitigate this was to slightly constrict the nozzle near the exit, which is why it's not in the typical parabolic form we expect in a vacuum nozzle. The RS-25 was also fully reusable. I think we tend to forget what an impressive feat this was for the early 1980s. Another design requirement that was required early in the shuttle development was the need to include the engines on the orbiter itself, so they could be brought back and reused. So we moved them from the external tank and onto the orbiter. Some have since criticised the time and cost required to rework these engines. But remember, the orbiter would have not made it to orbit without them. They had to be complex and expensive. The alternate option was to throw them away after each launch, and that's a crazy thought, isn't it? Rework was always a better and cheaper option. The Shuttle remains the only vehicle ever to bring Stage 2 engines back from orbit and reuse them. SpaceX may be near to doing so at the time of recording, but we'll see. This chapter is suspiciously long, isn't it? I wonder if it might be going somewhere. I've already hinted at the main drawbacks of using hydrogen as our main source of energy. It's comically low in density. That's why we need such a large external fuel tank. And this offsets some of the efficiency gain. That huge tank represents a significant amount of extra mass. What we need is a first stage that can loft our high-energy hydrogen fuel above most of the atmosphere, where we can burn it to gain as much velocity as possible. That way we lose less to gravity via the extra mass. The same applies to a lesser extent for air resistance. Burn as much hydrogen above the lower atmosphere as possible to minimise atmospheric drag losses. Saturn V achieved this with a kerosene-oxygen-fueled first stage. Using a derivative of the Saturn V first stage was considered early on, but deemed infeasible. This would give us a stack-up over 100 metres in height, with the orbiter piggybacking on the upper stage. It was considered, but I think we can all agree this would be borderline absurd. So instead, we looked to repeat our earlier approach. We strapped stage 1 onto the side of the hydrogen tank in the form of boosters. The F1 engine used for the Saturn first stage could possibly be used to carry us above the lower atmosphere, but here we run into a safety issue. Liquid-fueled engines are mechanically complex. Of the 13 Saturn V launches, 2 experienced second-stage engine failures, with Apollo 6 losing 2 engines. That's a 2% failure for all Saturn V engines. A shuttle would probably need 4 F1s at minimum to launch. I'm basing this on the back of an envelope estimate based on research for my next video. Losing one F1 would necessitate shutting down the engine diametrically opposite to maintain balance. For at least the first minute or so of launch, the weight of the launcher would exceed the thrust of the remaining engines, dooming the craft to fall back to Earth. And remember, there was no crew escape system. The orbiter could not detach from a full external fuel tank to escape either. I don't have time to discuss abort modes in full, but since the shuttle flew inverted to reach orbit, an external tank containing fuel would be pushed back into the orbiter, causing it to lose control and break up. Side-mounting the boosters provides a safety benefit in this respect. Were a more conventional vertical stack-up used, we'd be relying on those 3 highly complex RS-25 engines to ignite mid-flight. Failure to light would mean loss of crew and vehicle. With side-mounted boosters, the main engines can first be ignited and checked before we commit to launch. This pad abort capability was used on 5 occasions during the shuttle life. Again, this is all very back of the envelope, but let's be generous and assume a 1% chance of an F1 failing in the first minute of flight. With 4 of them, that would constitute a 4% probability of loss of crew and vehicle on every launch due solely to booster failure. The solution was one that has, in retrospect, become one of the most controversial design choices for the shuttle. I honestly believe this is an unfair assessment, as it's often not considered in the proper context. The shuttle used 2 SRBs, or solid rocket boosters, as its first stage. At first glance, SRBs appear to be a terrible choice for crewed spaceflight. There are 3 reasons for this. First, once they're ignited, they cannot be extinguished. For any other launch system, this would be a concern. Imagine, say, a Soyuz experiencing a problem at launch, but the crew having to ride out the problem for 2 minutes before aborting. The shuttle had no crew abort system, however, and remember, it was bound to that external fuel tank until all the hydrogen and oxygen were depleted. Even if it were somehow possible to extinguish an SRB, it wouldn't help the crew in the case of an emergency. The second is the nature of solid propellant. The shuttle SRBs used ammonium perchlorate oxidizer mixed with aluminum powder as fuel. This was held together with a polymer binder, giving an elastic solid mixture. Mixing fuel and oxidizer together is an absolutely horrible thought as an ex-oil and gas engineer, but NASA and Thiokol, who built the SRBs, were clearly able to successfully manage the ground handling risks, as an SRB was never accidentally ignited during processing. This is not true for the Brazilian Space Agency, who experienced one of the worst spaceflight-related disasters back in 2003, and that was due to an accidental SRB ignition. I'd argue hazards to ground crew would be the strongest argument not to use SRBs for the shuttle. The third concern is the rapid nature of some failure modes. During normal operation, the propellant mixture is burned along the length of the inside of the booster. There's a hole along the length of the propellant, and the inner surface of this hole is the reaction front. However, there are failure paths that can transform an SRB into the world's largest pipe bomb. A blocked nozzle or cracks in the propellant mix can cause an overpressure in the casing. Here's what that looks like. Again, for vehicles with a launch escape system, this would be a major concern. It's doubtful such a system could pull the crew free before being consumed by the explosion. But the shuttle had no crew escape capability. So, the obvious dangers of SRBs to the flight crew were generally not really applicable in the case of the shuttle. And the risk of an engine failure was significantly reduced due to the mechanical simplicity of SRBs, making them in principle a safer choice than liquid-fueled boosters. Let's now very briefly follow the design process for the shuttle's SRBs.
All NASA documentation regarding the SRB design is in US units, so that's what I'll use for the remainder of this chapter. The shuttle's SRBs were based on the SRBs from the Titan 3C. These were a well-respected design, with a total of 33 launches prior to the shuttle's first launch. At no point did a Titan 3C booster fail in flight. The boosters were comprised of 5 segments, joined by a Tang&Clevis field joint shown here. NASA did consider a single segment SRB for the shuttle, but the proposed design from Aerojet was deemed inferior to a competing proposal from Thiokol for a variety of reasons. Though field joint failures had not been observed on Titan 3C, Thiokol made a series of improvements for the shuttle SRBs intended to make them safer for crew. The most visible was the addition of a second sealing O-ring. The purpose of these O-rings was to seal hot exhaust gas within the SRB casing, ensuring it only exited through the nozzle. Exhaust leaking from the joint would likely lead to a loss of crew and vehicle. The second O-ring was accepted as a redundant contingency by NASA. At this point, I must clarify the relationship between NASA and their contractors. Prior to launch, every shuttle went through a flight readiness review. This was an arduous and comprehensive process involving 4 levels of management, plus some extra work groups. Level 4 reviews involved the individual contractors for the main engines, orbiter, tank, boosters, and other major systems. Level 3 was essentially the handover from upper management for these contractors to NASA at the Marshall Space Flight Center. Levels 2 and 1 involved NASA senior management signing off based on information provided by Level 3 managers. For now, we'll concern ourselves with Level 3 management. The process of testing and designing the constituent parts of the shuttle were highly adversarial. Contractors would be constantly challenged on designs and conclusions by Marshall, who demanded systems be demonstrated as safe even under extreme conditions. Only rigorous and evidence-based analysis was accepted as a demonstration of safe operation. Prior to the first shuttle launch, Marshall and Thiokol disagreed on the redundancy of the SRB joints. As the SRB motors fire, we see the boosters flex into an upright position. Marshall identified a rare and extreme case where this rotation could potentially lead to both the primary and secondary O-rings failing to seal for about 600 milliseconds. Thiokol performed 7 live firing tests along with extensive individual component tests to demonstrate this was not the case. Marshall actually refused to accept these results in full, pointing to differing measurement approaches. Thiokol implemented corrective action, which involved shimming the joints to ensure the O-rings would seal. As far as history shows, Thiokol engineers unanimously accepted this approach. Marshall internally certified the joint as redundant. In designing a system as complex as the shuttle, one inevitably arrives at the point where we need to do something either brave or spectacular. STS-1 was the first test launch of the shuttle, but NASA were forced to take the brave option. The shuttle didn't have full autopilot capability. The first flight required a crew. On the 12th of April 1981, NASA went from never having launched a single element of the shuttle to launching the full stack in one go. STS-1 presented a cacophony of issues. Installing the thermal tiles proved significantly more timely and difficult than anticipated. There were major concerns over the ability of the RS-25s to perform. During launch, vibrations bent fuel tank supports and broke an RCS support strut. On re-entry, the body flap was forced upward and almost led to a loss of control on landing. Heat shield damage was observed throughout, with buckling to the landing gear door, but no damage was observed to the SRB O-rings. STS-2 launched 6 months later, with extensive remediation for the issues encountered on STS-1. On return, damage to an SRB O-ring was identified. A point on the primary aft joint O-ring experienced 0.053 inches of erosion due to hot gas. This was a cause for concern, but nothing too unexpected. The shuttle was experimental at this point. The likely culprit was identified to be the sealing putty around the joint,
and with the agreement of all Level 3 managers, a new putty formulation was presented for future use, along with improved procedures for applying it. Consensus had been reached, and the issue was closed. STS-3 and 4 flew with no erosion witnessed on the O-rings. At this point, President Reagan appeared in a highly publicised TV appearance to declare the shuttle operational after just 4 flights. This wasn't something really seen with previous launch systems, which were always considered as essentially experimental or developmental. But this reinforced the perception that the shuttle was a fully capable system, able to reliably deliver payload and personnel to and from orbit. This also added an onus onto engineers to minimise change to the design. It was public knowledge that the shuttle was complete. Any changes would now carry a certain liability. Talk began of sending non-astronauts on the system. Of course, the first non-astronauts we sent to space were politicians. They just get everywhere, don't they? A Republican and a Democratic senator were sent on 2 separate flights, for some reason. Back at NASA, there was continued concern regarding flaws with the heat shield and the reliability of the RS-25s. Meanwhile, Marshall decided to downgrade the SRB joints from a redundant to a non-redundant designation. The shuttle had hundreds of non-redundant systems. That's the nature of spaceflight. They remained unconvinced that the secondary could seal under the worst possible conditions, so as per procedure, the joints were designated safety critical to make them more visible to level 2 and 1. Over the next few years, Thiokol engineers struggled to eradicate erosion in the O-rings. Increasing the test pressure between the seals appeared to fix the issue at one point, only for erosion to be witnessed again a few flights later. Likewise, improved putty formulation appeared to prevent erosion, only for it to reoccur again and in an inconsistent pattern. Design began on a new joint, but this carried its own liability. The existing joint at least had known flight and test history. Replacing it immediately would require a 2-year pause in shuttle flights, so it was developed in tandem with ongoing launches. Computer modelling was carried out to fortify the belief in a safety margin between observed erosion and that needed to cause a failure. The worst observed case of O-ring damage was in STS-51C. Not only was blow-by past the primary observed, but erosion was present on the secondary too. Hold on, this is me a day before releasing the video. That's a mistake. The flight with secondary O-ring erosion was STS-51B. STS-51C launched 3 months prior at an unusually low ambient temperature of 53 degrees Fahrenheit. STS-51C saw severe damage to the primary but no damage to the secondary O-ring on 2 field joints. STS-51B launched in an ambient temperature of 75 degrees Fahrenheit and saw a primary completely burn through and a secondary experience 0.032 inches of erosion. I made that mistake because the way flights and SRBs were numbered was inconsistent. Are you confused? Good, because as we're about to see, so were Marshall. Of course, this was a major concern for both Marshall and Thiokol. A launch constraint, which was a special condition to improve visibility to level 1 and 2, was placed on the joints and remedial action taken. Following extensive study, test pressures were increased and O-ring placement procedures were improved. The likely cause was identified as contamination to the surface of the O-ring. All levels of management accepted these changes and there were no signs of reservations from Thiokol engineers. A path did exist for engineers to directly raise problems to NASA senior level management. This path was never taken. During the second half of 1985, higher level management were probably more concerned with the near loss of STS-51F due to a main engine failure. STS-61C launched in the first week of 1986, and it narrowly avoided an in-flight abort due to issues with the LOX feed. On January 27, 1986, Marshall received an unexpected request for a teleconference from Thiokol. A number of SRB engineers were recommending a delay to the next day's launch. This was unprecedented. A contractor had never recommended a no-go out of the blue like this. NASA instinctively adopted a kind of informal Level 3 flight readiness review meeting, acting in their usual adversarial role. Haphazardly, both NASA and Thiokol gathered as many relevant engineers at their respective sites to discuss the issue. Now, I say engineers because everyone involved was an engineer. Some may be referred to as management, as those were the ones responsible for signing off Level 3 decisions, but everyone present was a qualified engineer. As NASA staff trickled into the teleconference, some of the charts on screen now were faxed across in a random order. 2 Thiokol engineers in general were vocal about delaying the launch: Roger Beaujolais and Arnie Thompson. They did everything within their means to stop the launch. A launch temperature of around 30 degrees Fahrenheit was forecast. The recommendation was to launch at no lower than 53 degrees Fahrenheit. That was the previous lowest launch temperature. Thiokol were far from unanimous in this decision, with engineers either staying quiet or voicing concerns directly to their managers who spoke on their behalf. Marshall were unimpressed. This was a shock. Thiokol had been happy to approve launches in temperature as low as 40 degrees Fahrenheit. Those launches had just not gone ahead for other reasons. Thiokol appeared to be discarding all prior recommendations. From Marshall's point of view, the evidence was shaky at best. Just a couple of data points. In fact, severe O-ring erosion had been experienced at far higher temperatures. And testing on the O-rings appeared to show resiliency down to 30 degrees Fahrenheit. Thiokol's sudden reversal was in contradiction to the evidence-based approach that had built up a precedence of safe flight over the past 9 years of booster development and launches. In maintaining an adversarial role, NASA were inadvertently challenging Thiokol to demonstrate the shuttle was not safe to fly. Given the lack of evidence, Thiokol management requested 5 minutes on mute to reconsider their evidence. The mute period lasted closer to 25 minutes. Marshall were fully expecting Thiokol to return and maintain their no-launch recommendation. In fact, NASA engineers discussed future cold weather mitigations for future launches during this period. Imagine their surprise when Thiokol returned with a reverse decision. The launch was to go ahead. There was no need to report to Level 2. Consensus had been reached. The issue was closed, as per procedures. The main concern on the morning of the launch was ice on the launch tower. NASA ran various simulations and calculations to assess the feasibility of ice striking the vehicle. By 11:38 am, the ambient temperature had risen to 38 degrees Fahrenheit, and the launch proceeded.
4%. Challenger, go at throttle up.
Roger, go at throttle up.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
During my second year of university, we were all forced to take an elective, non-technical module. I reluctantly chose an Ethics in Science and Engineering course. What a waste of time, right? I was there to learn how to be an engineer, not a bunch of philosophical nonsense.
In one of the first lectures, this book was suggested as optional reading. This is probably the most important book I've ever read. The Challenger Launch Decision by Diane Vaughan. It's literally the reason this channel exists. I carried the lessons from it into the first really popular video I made, even though I got a little snarky in that video. The account I've presented is based on Vaughan's retelling of the disaster, constructed after 10 years of research. And by the way, that ethics course is probably the one that has stayed with me the closest since I graduated. I firmly believe every engineering degree should include an ethics element. The way I presented that build-up is likely in contradiction to how you've heard it portrayed in the past. It was arrogant and irresponsible managers ignoring their engineers in a rush to launch, right? Following Challenger, a presidential commission, known as the Rogers Commission, was set up to investigate the accident and provide recommendations. The members of this commission are some of my all-time heroes: Neil Armstrong, Chuck Yeager, Sally Ride. There was Richard Feynman too, but we'll get back to him. To argue with the Rogers Commission would be to argue with God. But argue with God we shall. Well, argue's a bit strong. The Commission didn't get anything wrong as such. They just didn't explain why the launch decision was made. That wasn't really their aim. Though the Commission stopped short of blaming anyone for Challenger, the overall tone was clear. A rush to launch due to Level 3 managers overriding engineers. This is certainly the lasting impression the press and general public took away. The problem with this conclusion is it makes no sense and teaches us nothing. No one would approve a launch if they believed it was likely to fail. NASA had no issue postponing launches in the past, and not a single member of NASA or Thiokol tested to being pressured to launch on time. I haven't even mentioned the reason Challenger is so cemented in history. Here's the flight patch. See the apple? That's because Krista McAuliffe was a teacher. The winner of the Teacher in Space program. The launch was broadcast live to schools. The entire nation had been following her up to the launch. She'd become a nationally beloved hero at this point. My wife's a teacher, and so is my mother. I talk about Challenger in a clinical tone, but for some reason, that little apple on the launch patch almost makes me tear up. And I wasn't even born when it happened. I haven't mentioned her because there's absolutely no evidence her presence on board contributed to the decision to launch. Again, this may be in contradiction to what you've previously read, but that appears to be the reality. No one interviewed by the Commission stated McAuliffe's presence had any bearing on the launch decision. And why would it? The flight readiness review process was well established and incredibly thorough. I doubt there was even a feasible means to bypass it. Normalised deviance is the term coined by Vaughan for NASA and Thiokol's repeated ability to identify problems, assess and accept them. It's an insidious problem and becomes more and more difficult to identify the larger an organisation becomes. We still see it everywhere today. Even accidents that can be blamed on gross negligence often still have an element of normalised deviance. I've also touched on the structural secrecy and the culture of production at NASA that obscured problems and led to misaligned objectives. I don't have the time to go into detail on those elements. Read the book for a fuller picture. As for Richard Feynman, he's the most memorable member of the Commission, and was rather scathing of NASA in his assessment. His appendix to the Commission report contains some pretty salient lessons in risk communication. It also gives no concrete solutions for improving safety culture, which is unsurprising. Feynman was a theoretical physicist, not a sociologist. He famously demonstrated that rubber O-rings do indeed become stiff when they become cold. NASA knew temperature affected O-rings, so did Thiokol. The problem wasn't that no one knew this, it was that the relevance was obscured from them by mixed signals and numerous other unrelated problems, and an organisational structure not suited for risk communication. Now, I want to make something extremely clear. None of this exonerates NASA. Though the popular perception of arrogant managers not listening to engineers is not representative, the factors that led to the launch decision were much deeper seated, and NASA, and Congress for that matter, had allowed a culture of risk to develop unchecked over the course of a decade or so. And it remained largely unchecked following Challenger, as we'll see. This is a mundane reality. Everyone at both NASA and Thiokol followed their process to the letter. No one broke a rule. No single group can be held accountable for the disaster. There was no cover-up. There's no need for dramatic music or dramatic reenactments, because there was no one defined moment that caused the disaster. Had I been back there in 1986, I would have made the same decision as the NASA managers at Marshall, and you would have too. The common retort to this is something along the lines of, had I been in the teleconference, I would have stood up and unambiguously said, if you launch the shuttle tomorrow, it will be destroyed and everyone will be killed. What few fail to recognise is that no one on the call believed that was the case. The actions of engineers immediately after the call, and their later testimonies, heavily insinuate that although some believed the launch was an unacceptable risk, none believed it would result in the loss of crew and vehicle. Okay, there was one exception. Bob Ebling, a manager at Thiokol, was the only participant on the teleconference who subsequently testified he believed a catastrophic failure would be the result of the launch. One person out of 34 total participants. Due to the barriers we've already discussed, Ebling had no way of knowing he was the only person with this view at the time. After the disaster, he really beat himself up for not taking over the meeting and stopping the launch. He died in 2016, apparently still convinced he could have done something. Looking from the outside in, we know there was nothing he could have realistically done to prevent the disaster. I'd like to finish this chapter with something a little more uplifting. Barbara Morgan was the backup teacher in space. Had McCullough not been able to fly, she'd have taken her seat. She was at Kennedy and watched the Challenger disintegrate in person. Shortly after the disaster, she asked NASA to fly her on the next shuttle. Unsurprisingly, they refused and terminated the Teacher in Space program. Morgan then applied for astronaut selection and was accepted in 1998. She finally flew to the International Space Station aboard the shuttle in 2007 as a qualified astronaut. Almost immediately after returning to Earth, she quit and returned to a teaching role. Let's have a positive chapter before we blow up a second shuttle. After the last chapter, it'd be easy to assume the construction of risk for the entire shuttle program was flawed. I think that's how many of us see it in retrospect. But there were many aspects of the program that did an excellent job of identifying, quantifying, and mitigating risks. The example I'd like to discuss here is the avionics system. In the case of the shuttle, this was referred to as the Data Processing System, or DPS. What was the first operational aircraft to be controllable solely by digital fly-by-wire? Based on the topic of this video, you probably correctly guessed, it was the shuttle. NASA invented and developed digital fly-by-wire, in part for the shuttle. I have an entire video about it here. In fact, digital fly-by-wire was just one of the functions handed over to the DPS. It was also responsible for monitoring main engine health, controlling the vehicle on ascent, including the abort modes if necessary, performing on-orbit maneuvering and navigation, performing communications and tracking, payload operations, power distribution, and controlling the vehicle during re-entry. This was an extremely demanding set of requirements for the day, and it required a revolutionary avionics system. I talk a lot about fly-by-wire, but this was much more than just fly-by-wire. The centre of the DPS was an IBM AP101 flight control computer. These were far from cutting edge by 1981. The AP101 had been extensively tested by NASA as part of the digital fly-by-wire experiment. In brief, this involved fitting an F-8 fighter jet with an Apollo guidance computer to prove the concept. Then Phase 2 of the program replaced the Apollo computer with 3 AP101s. The modified F-8 was kept in service and used specifically to develop and test the code for the shuttle fly-by-wire system. So it's fair to say the computer itself was well-proven technology by the time the shuttle launched, and NASA were highly proficient at making the best use of it. The AP101 used magnetic core memory, which was practically ancient technology by 1981. However, again, it was considered more robust and reliable than the more recent solid-state memory. The 106K 32-bit words available, however, were insufficient to store the entire flight program, so the computer was connected to a tape storage device. During the relevant portion of flight, programs would be loaded from tape and into the core memory. The connection between the computer, mass storage device, external sensors, control surfaces, RCS thrusters, cockpit displays, and pilot controls were handled by an I/O processor. While the hardware itself wasn't particularly new, the requirement to place it between the pilot and the physical vehicle itself most certainly was new. So, how was the risk of failure handled? During most phases of flight, a failure of the DPS would mean the loss of crew and vehicle. Computers and electronics fail all the time, so NASA took what I consider to be a gold standard approach to redundancy. There wasn't one flight computer, there were 4. 4 identical AP101 units and 4 associated I/O units were housed in the avionics bay in the middeck. Each monitored the outputs from the other 3, and any outputs that deviated significantly from the others were discarded. The deviant computer could be automatically shut off if necessary. That sentence glosses over a multitude of specifics.
I recommend reading the Guide to the Avionics System in the sources. It's a masterpiece of redundancy design. Next, the tape storage. Code can become corrupted and tape drives can fail, so there were 2 of them. Each contained 3 full copies of the flight code, giving 6 copies in total on the shuttle. It was even possible to broadcast commands into memory from the ground in case of both drives failing, though with the limited bitrate this would be a slow process. So it looks like we've removed single points of failure from the avionics system. Not quite. How about an undetected bug in the code? Imagine a scenario where a coding error leads to all 4 computers giving an erroneous output. This is why I consider the DPS to be a gold standard for redundancy. There was a 5th computer. An entirely separate AP101 and I/O processor were present. This contained code entirely in memory that could perform minimal flight functions to get the spacecraft into orbit and to fly it back to a safe landing. The code was written by a separate and independent team, and in the case of a common failure in the primary system, this backup could be manually initiated to ensure a safe return. The DPS was replaced with more modern iterations throughout the shuttle life, and this initial system we've discussed wasn't without issue. On the first test flight, Enterprise's primary computer was knocked offline as the separation charges from the carrier vehicle fired. STS-3 had a rough landing due to pilot-induced oscillation. Both STS-8 and 9 had issues with the guidance program. But in all cases, the combination of NASA using previously proven technology and adding redundancy wherever possible ensured the crew made it home. I think something we easily forget is that NASA research is made freely available to everyone. So to create a chapter like this, all I had to do was pull up NASA's handbook on the avionics system. When I make videos on topics like Virgin Galactic, I can't go into anything like the level of detail I can here, because their material is proprietary. The shuttle's thermal protection system was a complete step change from anything seen before. The previous generation of capsules had used ablative heat shields, which were not only heavy, but also non-reusable. The lower surface of the shuttle, colloquially referred to as the heat shield, was composed of coated silica ceramic tiles. There were more than 20,000 of them, a considerable effort to glue into place, but they were reusable. The nose and leading wing edges were exposed to the highest temperatures on re-entry. These were shielded with panels of reinforced carbon-carbon. Both of these materials are extremely light and porous, but also brittle. They were glued to felt pads on the orbiter body to prevent damage via vibrations during launch. Each tile was printed with a unique identifier, so it could be glued to the correct location on the orbiter. Apparently, as the tiles varied in shape, these identification numbers could be fed into a computer-controlled manufacturing system to obtain a new identical tile. The upper surfaces of the orbiter were generally covered with flexible insulation blankets, as these surfaces were not subject to the same extreme temperatures as the underside. But mismanagement of that exposed heat shield was the cause of the second shuttle disaster. And I remember Columbia. I was being driven back from a high school cross-country race in February 2003 when the news came over the radio. Columbia was the beginning of the end of my childhood love affair with the shuttle. I haven't studied Columbia as extensively as Challenger, but the Plainly Difficult channel inadvertently did me a favour a few weeks ago while I was writing this script by making a full video on Columbia. As with Challenger, the technical overview can be done in just a few sentences. On ascent of STS-107, this happened. I first saw this video years after the disaster, and it's one of the few engineering videos I audibly gasped at the first time I saw it. The foreign object that struck the wing at over 700 km an hour and 82 seconds after launch was a piece of foam insulation from the external tank. For reasons we'll discuss, NASA were unaware this likely punched a hole through the RCC panel on the leading edge of the wing, one of the areas of the craft exposed to the highest levels of heating on re-entry. 2 weeks later, the craft disintegrated on re-entry, killing all 7 crew.
There's one question that's plagued me for 20 years, and if you've made it this far into the video, it's probably plagued you too. Could Columbia have been saved? The answer is simultaneously absolutely not, and probably yes. Probably yes refers to a fictional scenario where NASA quickly identified the threat and acted accordingly and appropriately. We therefore consider the technical possibility of bringing the crew back to Earth, using everything available at NASA's disposal. And let's be clear, this would be a blank check problem. I've got no doubt Congress would throw all the money necessary to save the crew. So let's walk through the options. There are two broad scenarios. Option 1 would be an on-orbit repair. STS-107 was not fitted with the Canadarm, so the first step would be to spacewalk and perform an inspection of the damaged area. This would not be without risk. It had involved 2 astronauts performing an unscheduled excursion. They'd clear the payload bay doors with one acting as a bridge for the other to access the wing leading edge. The surfaces on top of the doors are radiators. Damage those and it'd be emergency deorbit. Next, a second excursion would be performed to effect a repair. This had involved detaching the ladder from inside the crew compartment and tethering it to the wing root. Materials would be scavenged from the shuttle and possibly the Space Hab module, which was also carried on STS-107. The broad aim would be to use titanium plates and possibly heat tiles recovered from elsewhere on the shuttle to seal the gap in the leading edge. Water would be used to hold the materials in place as it would rapidly freeze in the vacuum of space and act as a rudimentary adhesive. Of course, this repair excursion would be risky and of questionable effectiveness, but we must always remember the alternative was certain death. With a lack of other options, high risk of failure is infinitely better than certain failure. Option 2 would be even more audacious. Coincidentally, a second shuttle was near launch readiness when Columbia was in orbit. Atlantis was being prepared to launch for the STS-114 mission on March the 1st. The latest Columbia's crew could survive with the onboard supplies was about 4 weeks. That's until February the 15th. Could Atlantis have performed a rescue mission? Let's go through the sequence of events that would need to happen to make that possible. First, Atlantis would have to be rushed through all the pre-launch checks. We've already discussed how extensive this process was. Some checks would have to be skipped, and of course Atlantis would be flying with the same issue that Columbia did. There was always the possibility of a second foam strike, leaving NASA with 2 damaged shuttles in orbit. Next, a crew would have to go through a rushed training and rehearsal schedule for the rescue mission itself. We may consider sending just 1 or 2 crew up to perform the rescue, but that would be impossible. 4 were needed at a bare minimum. 2 to perform the spacewalks, and 2 to maintain station keeping between the 2 spacecraft. There was no way around that. A rescue mission would put 4 additional crew members at significant risk. Assuming the shuttle could be prepared and a crew readied, NASA would then depend on favourable weather during the 3 available launch windows. Assuming all went well, Atlantis would rendezvous with Columbia and position itself back-to-back with the damaged orbiter. 2 crew from Atlantis would undergo the first spacewalk to establish a tether between the craft and pass over lithium hydroxide canisters and spacesuits for the crew. Over the course of many hours, the crew of Columbia would don spacesuits and make the trip between the 2 orbiters, sending the suits back to Columbia. An electronic data cable would be run between the flight deck and mid-deck of Columbia, allowing ground control to remotely deorbit the spacecraft over an uninhabited area. With 11 crew in Atlantis, some would have to be strapped to the floor for return to Earth. Had NASA pulled this off, it would have been comparable to, if not more impressive than bringing back the crew of Apollo 13. I rushed through that scenario, and even then, everything would have to go right for it to be a success. Putting a second crew at risk to rescue the first would be an incredibly hard sell, but just imagine. Now, these two options are often presented in isolation, but there were other potential actions on the table. The first could only be applied to the on-orbit repair option. Try to reduce the demands on that repair. There are at least 3 actions that could be taken here. All seek to reduce the amount of thermal energy the wing was exposed to. The first would be to initiate re-entry from a lower altitude. STS-107 was already pretty low as far as crewed orbital missions go, around 275 kilometers on average. It would be possible to first drop to a lower orbit before initiating a second deorbit burn to begin the re-entry. This would slightly lower the re-entry speed, but not by much. It'd have little chance of saving Columbia by itself, but also carried virtually no risk. The second would be aggressive load shedding. Unwanted mass would be dumped from the vehicle in a series of spacewalks. That'd include the space hab module, excess supplies, and anything else with significant mass. Less mass would mean less kinetic energy to lose via re-entry, reducing thermal loading. This would be a risky option due to the need for unscheduled spacewalks, but again, high risk is better than certain death. Were these two options employed, they may have been combined with a modified re-entry profile, where the orbiter re-entered in a kind of side-slip attitude, reducing flow across the damaged section. I have no idea how feasible this would be, or how much it could potentially reduce the overall heat loading. It would increase heat loading on the undamaged wing, though. A final family of potential actions would be an emergency resupply. This could either be used to get more supplies to the crew, allowing more time to prepare a rescue with Atlantis, or a more suitable repair kit could potentially be shipped. An appropriately shaped titanium plate, some RCC tiles, and adhesive may have been all it would take. The first option many may jump to would be the Russians. They usually have a Soyuz knocking around at Baikonur. Unfortunately, that would be impossible. Due to the relatively high inclination of Baikonur, a Soyuz would be unable to reach Columbia. There was another viable option, though. An Ariane 4 was present at the ESA launch complex in French Guiana. This was due to launch a communications satellite on the 15th of February. Potential options could range from strapping equipment to that satellite and just launching it at Columbia, to kludging together a crewed resupply vehicle. Either way, the launch vehicle would require an expedited launch and reprogramming to rendezvous with Columbia. Whatever vessel was launched would have to be accessible via spacewalk, which would carry many, many conditions that I won't get into. This would be a Herculean task, but not necessarily impossible. The Ariane was the most versatile launcher available, but there were at least 2 more. We know because NASA launched 2 other spacecraft from Cape Kennedy while Columbia was in orbit. One was a Delta II, which would probably be even more difficult to modify in such a short time, but had the advantage of being on site. The other was a Pegasus light launch vehicle. Though only capable of launching 500 kilograms to LEO, this may have been enough. The resupply options sit on the edge of feasibility, but they represent at least 3 potential options, none of which required an additional crew to be put in danger. In conjunction with everything else discussed, there were many options on the table. In an ideal world, many had been pursued and one would have been successful. And so we come to the second part of my answer. NASA could not save Columbia's crew. We know they couldn't because they didn't. In order to open up any of those options, NASA would need to recognise that the crew were in danger. And in order to do so, they needed to inspect the damaged area of the orbiter. The relevant teams were aware of the foam strike, and for that matter, so were the astronauts. So rumours they kept it quiet because they knew the situation was hopeless and nonsense. But following a handful of meetings, they decided imaging via either a military satellite or ground station was unnecessary. The path to a rescue was closed from the start. Just 2 flights after the Challenger disaster, Atlantis suffered extensive heat shield damage. A further 64 launches had been observed to experience foam strikes. 6 of these involved the bipod foam ramp, the same piece of foam that doomed Columbia. The plainly difficult video on Columbia originally had a title along the lines of NASA made the same mistake twice. And I agree with that sentiment. By following the recommendations of the Rogers Commission report, NASA made many excellent safety improvements to the shuttle. They also failed to correct the underlying culture which allowed deviances to be normalized. Looking at this video in isolation is shocking. Viewing it in 2003, engineers would have seen something they grew accustomed to. They followed proper process, discussed the problem as required by established procedures, and came to a consensus. Columbia could never have been rescued because NASA's organizational structure in 2003 made a rescue impossible. Vaughan's book was released 7 years before Columbia. The final few paragraphs strongly imply that the organizational structures that led to Challenger were still in place, and had in some cases been exacerbated by applying some of the recommendations of the Rogers Commission. This video was supposed to be a defense of the shuttle. I've spent more time discussing the times it killed people than the actual benefits. And that's for a reason. The shuttle was deeply flawed, but I think we forget too often what it gave us. Before the shuttle, US spaceflight consisted exclusively of men being strapped into tiny capsules. It was solely a field of exploration. The shuttle made spaceflight routine. It became a space for researchers, engineers, and sadly for a brief period, politicians and teachers. NASA's willingness to believe the system was safe enough to send a teacher into space was arguably the shuttle's biggest flaw. The shuttle trapped us in low Earth orbit is absolutely something I used to say a few years ago. What would the alternative be, though? To send a crew to Mars or on a Venus flyby? Another high-stakes and showy exploration mission with questionable benefits to the rest of us? To get to the moon, NASA first had to learn how to walk in space, and that was the purpose of Gemini. Now we have the International Space Station. Building on the success of Mir, the ISS has taught us to work in space long-term. If we want a moon base, we'll need to store cryogenic fuel long-term. We first did that on the ISS. We'll need long-term water purification, tested on the ISS. Learn how to work and live long-term in space. ISS. You get the point. I absolutely do not have time to go through the benefits research conducted on the ISS has given back to us on the ground. But unlike fixed goal projects such as Apollo, a sustained presence in low Earth orbit has opened up space access to anyone willing to take it. If you have a ham radio license, you can even talk to the astronauts there right now. Without the shuttle, there would be no ISS. I feel privileged that my first memory of a major news event isn't of some major tragedy. It's of my dad showing me photos of Jupiter from the Galileo probe, which was launched from the shuttle. It launched Ulysses too, arguably one of the most interesting interplanetary probes ever built. But aside from the ISS, the shuttle will probably be best remembered for Hubble. Not only did it launch it, but it revisited it a further 5 times. I grew up marvelling at the Hubble images, and I still do, because Hubble is still functional to this day. Honestly, it's a strong candidate for the greatest scientific instrument of all time. Something else I used to say was the private sector could do a better job than the shuttle. Putting aside the fact that no one's built anything that remotely approaches the shuttle's overall capability and versatility, could they? From scratch? Where does Starship's thermal tiles come from? Where did the design of Ariane 5's huge SRBs originate? How were the recovery procedures for Falcon 9's reusable booster developed? Where did the avionics and guidance system for New Glenn come from? How were Rocket Lab able to get hold of data to develop their new engines? How was Dragon able to dock to the space station so seamlessly? Where did the aerodynamic simulations for Dream Chaser's lifting body start life? The shuttle. Without the shuttle, these systems wouldn't exist, or certainly not in their current form. I'm still a big advocate for private spaceflight, but developing a launch system from the ground up is unlikely to be a profitable endeavour. NASA needed to open that door for everyone else. The shuttle was expensive, but spaceflight is expensive. It was also the first reusable spacecraft, was the first to reuse boosters, it was the first system to reuse its main engines, it could carry a wider range of cargo than anything seen before. It could carry 8 crew to orbit in one go along with that cargo, feats still unmatched. It could catch and return more from orbit than any other operational system. The shuttle demonstrated the first of many capabilities that largely remain unmatched to this day. I really miss it. Thank you very much for watching. If you really like what I do and want bonus content, early access, and your name at the end of my videos, a link to my Patreon is in the description. Now, when I say the shuttle's capabilities are still unmatched, that's not technically true. There was one spacecraft that flew, and in an alternate universe may have competed with the shuttle. Problem is, it only ever launched once. I'll be back soon with a video all about it.